Okay. Yeah, I'm glad to announce now Dietmar Gruber from Montanuniversität in Leoben, an expert on fracture mechanical examinations, for sure. And he will lead us through this area of microstructures and the mechanical expression. And yeah, thanks, Dietmar, for coming.
Thank you, Thorsten, for this kind introduction. First of all, I would like to mention that the university changes the strategy and is now called Technical University of Leoben. So it is a good opportunity for us to spread this news. So if you hear that, it doesn't matter. It's a quite recent decision from the management. So a short introduction about me. I'm doing research on thermomechanical behavior of refractories. This means the testing of refractories, but as well simulation and especially finite element simulation. And what do we simulate? We simulate fracture tests and the lining behavior as well. So, okay. So what do we discuss today? First of all, I would like to talk a little bit about brittleness, because there are many different ideas about it, and maybe we come to a same understanding for it and how it relates to thermal shock resistance. And then the importance about the stability of crack propagation for determination of the material properties. The advantages of the wedge splitting test, a test which is standardized in the moment and used more and more in the whole industry and in the universities as well. Then the example of an inverse evaluation for this wedge splitting test, and how does creep, so the time-dependent information, influence the evaluated parameters. So, and if you now think, wow, what is he talking about? I have no clue what I can expect. Then I hope you are in the right session. I hope after the presentation, you will know more about it. So why do we need fracture mechanical testing of refractories? There's, first of all, we have the quality control. So you have to do it according to the standards after the production process to know which strengths your materials have. Then you need it for material development, for sure. You would like to know which strengths your material have, you develop. And then there is one section I call parameter determination, with the goal to have input parameters for your calculations. So if you would like to have an idea about the thermal shock resistance, if you would like to have an idea about the stresses you will have in the application in the refractory material, and if you like to have the parameters for a finite element simulation, then you need these parameters. You need to do the fracture mechanical testing at the different conditions you have in your linings. And I put it here as one. No, I don't know what's going on. Okay, I put it here as one single point thermal shock resistance. I will go a little bit more in details for this one afterwards. But first of all, I would like to discuss with you a curve like you see it here. We have a force and a displacement. This is a result from a fracture mechanical test. What we see, we start at the beginning, then we increase the displacement, we record more force, and then for sure we have a maximum. We reach it, and we further increase the displacement, and then we see that the necessary force for the further displacement is decreasing. So why is this important? What we see here, the area under the curve, is the energy which is consumed for the fracture process. And main part of the energy is consumed after the maximum of the load displacement curve. So if we would like to have an accurate representation of the energy consumed for the fracture, we need to register the whole curve. What does it mean now for us? If we would do a force-controlled loading, then the test would end here at the maximum force. Why? Because the machine is further increasing the force with a defined rate, for example, in newtons per second. And then we reach a state where the sample is not stable anymore because we further increase the force. Fracture would happen. In this case, then a diagram would look like this, that we reach this point and then we have an immediate fracture. No further displacement can be applied. What we learn out of it, to determine an energy, we need to have a displacement control testing. So one important point, one important takeaway, maybe for you, because many discussions I did in the past to explain this fact. So what do we need to know about the stability of a fracture is? Here, very simple drawing, we have the force over the displacement again. And if you now assume we do a tensile test, we start at 0 again, force is increasing, we're reaching the maximum. And if we have an unstable fracture, we have an immediate decrease of the force to 0, unstable, brittle fracture. Then we could have a semi-stable fracture represented by the blue curve. So we have a short contribution from unstable fracture, and then it's turning to a stable one. And the green curve represents the stable fracture. As described before, to determine the energy which is required for the fracture, we need to have a stable fracture. And what is now influencing the stability of a fracture process in our sample? And basically, there is one important number. It's called the brittleness number. And how is it calculated? It's a relation between the elastically stored energy in the sample in the testing machine divided by the irreversible consumed energy. This is the work of fracture, which is necessary to fracture your sample. So it could be a tensile test or a wedge splitting test as well. And how is this brittleness influenced? Influenced by load, geometry, and material parameters. If we go a little bit more in details now, we have again this simple load displacement diagram from a tensile test. We start at 0, we increase the displacement, we reach the maximum force, and in this example, we have a stable fracture with a linear softening behavior of our material. And if we do now these calculations, so that we make a relation between the elastic energy and the work of fracture, then we can start like this. We have the force multiplied by the displacement at maximum force, and we divide it by 2 because the area of this triangle here is the elastic energy in the moment of the fracture. And this we divide by the work of fracture. So and then we can replace, we can use the strength of the material, multiply it with the cross-section of the crack to replace the force. And then we can replace this displacement by the length of the sample in the strain at maximum force. And we can replace the work of fracture by the specific fracture energy multiplied by A. Specific fracture energy is the energy per unit area which is consumed. And in the end, we're getting a relation which is squared the tensile strength multiplied by the length of the sample, in this case, length of the tensile test, and divided by the specific fracture energy multiplied with the Young's modulus. And this is, so to say, the balance between elastically stored energy and work of fracture for a tensile test, and describing then the brittleness of this tensile test. You see, if the tensile strength is increased, then we have more brittle behavior. It's even very more brittle because it's squared. if we have a higher work of fracture, then we have a less brittle behavior, so fracture is more stable. So from this calculations then in the literature, it was somehow a conclusion to calculate the brittleness number B like this, with the tensile strength squared with the geometry parameter. For a tensile test, it would be the length of the test, and then divided by a specific fracture energy multiplied with the Young's modulus. And as you see here, there is the age, which is the length of a sample. This means it's not a material parameter. It depends also on the size in the application. But we can also calculate here the so-called characteristic length, which has the dimension of a length from the specific fracture energy, Young's modulus, and the tensile strength square. This means high characteristic length is low brittleness. So very nice. Here with the characteristic length, we can compare materials. We get an idea how brittle the fracture will be. But the question is now, how can we determine all these parameters we need here to get an idea about the brittleness? And that's why I would like to discuss and introduce the wedge splitting test. Many of you, I'm sure, know it already, but I'm also sure not all of you. So what do we see here? We have a cubic sample, and here you see a wedge, which is then pushed downwards from the testing machine, and you see here rolls in contact with load transmission pieces, which transport then the load, the vertical load, which is applied here, to a horizontal force acting then on the sample. And this horizontal force is then splitting the sample. The crack will initiate here and propagate along the side notch through the sample. In the end, then we have the two totally split halves of the sample, and we can record the complete energy which is required to split the sample to have a complete fracture process. So what is now the advantage of this test? First of all, the fracture surface we generate when we split the sample is relatively big compared to the volume of the sample. This is important because as larger the volume of the sample, as higher is the elastic energy stored in the sample. And as more elastic energy we have, as higher is the brittleness number in the end. So this helps to have a more brittle fracture for the same material. And the other very beneficial fact is the relation between the forces, because here you see how we can calculate the horizontal force then from the meshing force, and for an angle of roughly 10 degrees, then we have a factor of 5. This means the horizontal force here is 5 times higher than the vertical force in the machine. And this for sure decreases the elastic energy in the machine, again making fracture more stable. How can we then evaluate the test? We see here a load displacement diagram, again with maximum force and then with the softening behavior. And we have this area under the load displacement curve, which represents then the energy consumed for the fracture process. How is it then calculated? Specific fracture energy F is 1 times per A. So this is the cross section of the fracture surface. Multiplied with the integral over the load displacement curve. So we integrate the force FH and multiply it here with the displacement. Additionally, we can calculate a strength value, which is called the nominal notch tensile strength, where we use the maximum force from the load displacement diagram and multiply it then with this term here, which I would like to explain on the next slide. So how is this part composed? We have the maximum force divided by P times H. P times H is the fracture area you see here in gray, plus, so this is coming from the tensile load, plus a bending load, which is then calculated by the normal distance y from the load application point to the center of gravity of our fracture surface, and divided by the resistance moment of this shape. So this means we assuming here that the stress distribution is a combination of a tensile load and a bending load in the sample. And then we are calculating this nominal notch tensile strength. So now you may ask, is this assumption that we have this combination of tension and bending, is this justified? And the question is not that easy to answer, but what we could do a finite element simulation and simulate the stress distribution in the sample. And this is what you see here. We have a model of the wedge splitting test. Here again, cubic sample. Then we have the load transmission pieces. We have the wedge moving downwards. And then we assume here in the center, we have a cohesive interface. This means here the crack can propagate. So we assume this behavior to these cohesive elements here in the symmetry line, where we say, okay, when the stress increases, then we have a strain in these elements, we reach a maximum strength, and afterwards we have a softening behavior. The area here under this curve is the specific fracture energy. So this means we can then simulate a crack propagating through the sample and receive a load displacement curve, as you see it here, where we have this maximum load, and then the area under the curve is represented by the work of fracture. It means GF times A, specific fracture energy, multiplied with the cross-section area. What I would like to mention here is, even if we have this peak for the single elements, in the end, summary of the fracture of all the elements gives this a curve without sharp peak. Why? Because fracture starts at the top element and propagates through the sample, and the peak is reached in consecutive order. So the peak is first reached for the first element and then later for the lower elements. That's why then we are getting this nice round shape, the load displacement curve. So, okay, we did our simulations. Now the question is, you remember, we have been thinking, is this assumption for the nominal notch tensile strength, is it justified or not to have a combination of tensile and bending loads? And what we see here is first part of the answer to this question. We see here the stress in the symmetry plane of the sample, and this is the bottom. Here's the support of the sample, and this is then along this fracture surface. It means the crack would initiate here and then propagate downwards. And here we are at the moment where the crack did not initiate. So before the crack starts to propagate through the sample. And we have here in this reddish color, we have the theoretical stress distribution according to the assumption for the nominal notch tensile strength. So this means have a superposition between tension and bending. And then we have the simulated stress distribution in the finite element model. And what we see here is that there is a significant deviation between this theoretical assumption and the stress we have in reality. I say to my simulation now reality, because it's for sure more accurate than the other assumption, where we have a much higher tensile stress close to the top of the fracture surface. So what is the reason? The reason is simply that we have a starter notch and around the notch we have a stress concentration. And that's why then we have this increase here. And in the bottom, the sample is resting on a support. That's why we have then higher compressive stress here. How does it look like later? So we have now the crack already propagated, you see, to this 20 millimeter mark. That's why the stress in the simulation decreased already. It decreased most at the top where the crack initiated, because here we have already the highest strain and the highest displacement, but it still did not decrease to zero. So there is no completely open crack. And then you see in comparison here, the stress distribution from the assumption for the nominal notch tensile strength. So we see there are significant deviations. And if we would then say we take the nominal notch tensile strength as a representative for the tensile strength, then we know it's not accurate. And how is it not accurate? We can see here in this diagram, where I plot the result for this relation, nominal notch tensile strength to the tensile strength, and over the brittleness. And you see for very low brittleness that the nominal notch tensile strength overestimates the tensile strength. And for very brittle materials, it underestimates the tensile strength. So now somehow we know, okay, nominal notch tensile strength is a parameter which does not represent the tensile strength. We know we have these deviations. How can we deal with this problem? And one possibility is now to again use a simulation to determine accurate values. How is it done? We take the result from the wedge splitting test, load displacement diagram. You already saw that. But then we do additionally a Young's modulus measurement to have this input Young's modulus of the material. And then at high temperatures, we can say, okay, there is also this deformation under constant load, which is called creep. This may also play a role. So we do these measurements before so that we have this data. And then we start an inverse evaluation to determine the specific fracture energy, tensile strength, and the strength of the behavior. How does it work? We have our sample produce a finite element model, for example, with the commercial software Abacus. We have an initial guess of our parameters, do the simulations, obtain the load displacement diagram. We do then a discretization of the load displacement curve and compare it then with the experiment. Then we see how far we are, so how close we are. We define a convergence criteria. If we do not fulfill it, and then we estimate with a solver a new parameter set and go to the simulations again. So until we then observe convergence and then have our results. How does it work? You see that here for a magnesium chromide product, we have here the force over the displacement again. And if you look here on one curve, on curve 1, you see the experiment and the simulation fits very well. And we are receiving here then this parameter set. Now I would like to discuss it a little bit. From the nominal notch tensile strength here, we got 8.7 megapascal. And for the tensile strength from the inverse evaluation, we're getting 5.5 megapascal. So you see it's a significant difference. Also, for the specific fracture energy, we see here 152 Newton per meter or joule per square meter, as you like it, and 178 from the simulation. So what is the difference here? You see from the experiment, we can only integrate the curve until we end the test. But for the simulation, we observe a higher value because the simulation assumes that we are going to the end. So from the input value, and then we are considering the whole curve. What does it mean now for the characteristic length if we have these two different parameter sets? If we take the parameters from the experiment, we are getting 163 millimeters, and from the inverse evaluation, we are getting 477. So it's completely different. So these have been room temperature experiments and evaluations. We can also simply do this test at high temperature. You see here a magnesium carbon sample in the furnace with the heating elements, a thermocouple for temperature measurement. Here you see the linear support and the wedge with the rolls for the load application. And then again, wedge is pushed down to split the sample. You see here already is the sample after the test. You see the crack already propagated through the sample. If we do it at high temperature, then again, we could do our inverse evaluation. You see in red the experiment, in blue the inverse evaluation. Again, there's a good fit. We can apply here for the softening behavior an exponential law, how it is implemented in Abacus already, and see that we can get a good fit for high temperatures as well. But this is without considering creep. If we now consider creep, because the sample is loaded at high temperature, during the test, creep will happen as well. And if we consider it in the simulation as well, then we see again, the fit is quite good, but the specific fracture energy determined with creep is significantly lower than in the case without creep. Why is this the case? Because the sample is deforming due to creep during the test. A creep is contributing to the area under the load displacement curve. So we need less additional work of fracture to fill the whole surface under the test, to fill the whole surface under the load displacement curve. And that's why then this value is with creep is lower than it is without creep. And how much it is? You see on this table, without creep, we are getting 563 newtons per meter, and with creep, 470 newtons per meter. Again, significant difference. What is important to know is, for all of you doing this test, especially at high temperatures, the contribution of creep depends on the speed of the test. So, because creep is time dependent, if you have more time, then you have more creep. So be very careful if you do like this, because if you do a very slow test, then you will get very low specific fracture energy, but a huge contribution from creep. For the tensile strength, we see that with including creep, we are getting a higher tensile strength. Why is this the case? Again, because of the contribution of creep, we need more strength to reach the same maximum in the curve. Yeah, and then we can again calculate the characteristic length for the cases with creep and without creep. And again, we see a significant difference. So at the beginning, I was mentioning the thermal shock resistance and how this relates to the brittleness and the parameters we determine. And without going deep into the literature or in the theory, I would like to discuss two simple cases. So we have two ideas, one from Kingery, the other one from Hasselmann, to increase the thermal shock resistance. So Kingery said, okay, I have an idea. I would like to avoid the crack initiation, like you would do it for French ceramics usually. And what is my idea behind it? I make a relation between the elastic strain. So R represents a temperature difference in a plate. alpha here is the thermal expansion. So if I then multiply R with alpha, then I have here the thermal expansion. And on the right-hand side, I have the tensile strength divided by the Young's modulus, which is the fracture strain. Yeah. So he says, okay, if my thermal expansion equals the fracture strain, then I have fracture, and this I would like to avoid. So it's about the strain. Hasselmann did a different thing, and to make the explanation short, I show you this one. We have the characteristic length we have discussed before, and this is equal 2 times this Hasselmann parameter. So he made, as we discussed before, a balance between the energies. So Kingery said, okay, strain balance, and Hasselmann said energy balance. And what does it mean then? In this case, we have the resistance against crack propagation from Hasselmann, and Kingery says, okay, we have the resistance against crack initiation. And these are two completely different things. So because in case of Hasselmann, you can have initiated cracks, and he would like to avoid that these cracks already there do not grow. So he uses the resistance of the crack to propagate. So these are the ideas and what is now relevant for the refractories. So if we look here again on our diagram, then we see maximum force is much higher for the black curve, for the magnesia refractory, and the maximum is lower for the magnesia spinel refractory. So on the first glance, people might say, okay, I expect a higher thermal shock resistance for the magnesia refractory because we have a higher maximum force. And then some people may think about the area under the curve. If you compare then this one for magnesia and this one for magnesia spinel, yeah, you may get an idea that maybe it's more or less similar. So maybe the magnesia refractory is more thermal shock resistant. If we look now on our parameters, then it looks different. We have here the line for the magnesia refractories, where we see a tensile strength 7.8 megapascal, quite usual for a magnesia brick. We have specific fracture energy 211 joule per square meter, and then we have this characteristic length 366, and the Young's modulus 106. For the magnesia spinel, we have a much lower strength, 2.1. 2.1 megapascal is not much. We have a little bit higher specific fracture energy, but I would say not significantly higher, but a much higher characteristic length. What does it mean now? If we calculate R, the Kingery parameter, and the Hasselmann parameter, we see here for Kingery, for this parameter set we have for magnesia, on that we need only a temperature difference of 3.7 Kelvin to have crack initiation in our refractory product. And if you think now about the applications we have and the temperature differences in the linings, in the refractories, you may have an idea that we cannot stay below 3.7 Kelvin. No? So this is somehow absolutely impossible. So in any case, we will have crack initiation. Surprisingly, for the magnesia spinel refractory, this value is higher. It's 7 Kelvin. Why? Because of the influence of the Young's modulus. So Young's modulus is 5 times lower, roughly, for the magnesia spinel. If you look now on the Hasselmann parameter, which is proportional to the characteristic length, we see that this value is much higher for the magnesia spinel refractory. And this is in the end then a reason why this family of refractories is applied, for example, in the cement rotary kiln, where we need the flexibility of the bricks during turning of the rotary kiln, or for example, magnesium spinel bricks on the RH degasser, where we have this extremely harsh thermal shock conditions. What do we learn now for refractories? If you do not have the chance to increase the strength so far that you can avoid crack initiation, then it's better to have a lot of resistance against the crack propagation. And this is what the industry is doing. And I hope I could increase your understanding. Why is this case? Why this is the case, and why high strength is not in any case an advantage. Thank you.